As you can see, this course is actually split into 3 main parts. Part 1, Part 2, and Part 3. So Part 1 deals with regular languages. That corresponds to Chapter 2, 3, 4. We then talked about context-free languages, Chapter 5, 6, 7, 8, and then Turing machines, Chapter 9, 10, 11, 12. And there is this kind of preliminary chapter, Chapter 1, which deals with general languages. So you can expect questions about all these topics. So the final is going to be kind of similar format to the midterm. And it is going to be longer and it's going to cover all the topics. So if you look at it at a high level, then there are many things repeating. So kind of the idea behind these 3 big sections of the course, they overlap. So we normally study a class of languages by first describing its definition in terms of one object. Like for regular languages, it would be DFA. And then we see alternative representations, like NFAs, regular expressions, and so on. We study closure properties, and we study techniques to prove that certain languages do not belong to that class, like pumping lamp. So the same kind of idea is repeated for context-free languages. We give different ways of recognizing context-free languages and proving that language is not context-free, and for Turing machines, where we distinguish between recursively enumerable and recursive. So the multiple choice are going to be worth roughly 2 to 3 times what the written part is worth on the final exam. So you don't want to spend too much time on the written part, but still written part is a significant chunk of points, so pay attention to it. Okay, so in terms of main topics, for general languages, of course, you should be familiar with different kinds of notations, how to represent languages in terms of, say, set builder notation, or in terms of different language operations, such as concatenation, reversal, union, intersection, star, plus, power, and so on. There are many corner cases for the languages. So in particular, you can consider an empty set to be a language, set of all strings. What happens when you take a language and raise it to a power 0, and so on. In terms of cardinality, we talk about linear size sets, exponential size sets, finite sets, infinite sets, and infinite we distinguish between countably infinite and uncountably infinite. I see some questions about whether these slides will be posted. Sure, I can post them after we discuss it today. Okay, for regular languages, we have the following 4 different representations: DFA, NFA, regular expression, regular grammars. You should know the definition of each and how to convert between them, and be able to come up with a description, a representation of a given language in terms of this. And the main theorems include equivalences between different representations, pumping lemma, and closure properties. So typically we ask questions on these kinds of topics. Okay, for context-free languages, again, as you can see, structure is similar, but context-free languages, we go a little bit deeper into them. So we only have here 2 kinds of representations, non-deterministic push-down automata and context-free grammars. When we discuss normal forms, we have 2 normal forms, Chomsky normal form and Greibach normal form. Each language without, if you don't consider the lambda issue, can be represented in Chomsky normal form. It can also be represented in Greibach normal form. Now, for Chomsky normal form, we give an algorithm how to convert any CFG to a Chomsky normal form. And that involves these simplification rules, like removing nullable variables, removing unit productions, removing useless productions. And you should remember the order in which to do them. Actually, the order is not stated correctly here. If you consider the order, you first get rid of nullable variables, then you get rid of unit productions, and at the end you get rid of useless variables. Okay, so now for context free languages main results, we have equivalences between CFGs and NPDAs, non-equivalence of NPDAs and DPDAs. So determinism actually loses some power. If you insist that your PDA is deterministic, there are some languages which it cannot accept, but NPDA accepts those languages. So you should remember typical examples. So which would be, for instance, A to the N, B to the N greater or equal to 0, union A to the N, B to the 2N, N is greater or equal to 0. And another example would be W, W reverse, where W is AB star. So there is a pumping lemma, ambiguity, and ambiguity has essentially two definitions, what it means for a grammar to be ambiguous. Grammar is ambiguous if blah, blah, blah. And inherent ambiguity. Inherent ambiguity is a property of a language. It is a property of a language. We talked a little bit about parsing, different kinds of parsers. One parser which is just kind of brute force parser, and another one we quickly mentioned, CYK membership. Okay, conversion to Chomsky normal form, and of course closure properties. And here you again need to be careful because context-free languages, they're not closed under intersection, not closed under complement. So that's the difference with, say, regular languages. So not closed under intersection and complement. However, now here you have this new property where it is closed under regular intersection. Regular intersection, and regular intersection simply means intersection with the regular language. Okay, now going to Turing machines, you of course need to know very well the formal definition and the standard model. You need to know about variations of the standard model because we can ask you some questions about variations of the standard model, but probably not too detailed, but you need to understand how the conversion might happen in certain cases and whether if you apply these particular variations, like say semi-infinite tape or two-dimensional tape, things like that, they don't change the expressive power of the model. Now, recursively enumerable languages, it is our standard definition of acceptance for a Turing machine. So there exists a Turing machine M such that L of M is equal to the language L. Recursive languages, it means that there exists a Turing machine M such that L of M is equal to L and M holds on all inputs. So your machine should never enter an infinite computation. Okay, definition of linear bounded automata. It is essentially a Turing machine using linear space. And here linear means in the size of the input. You need to know the Chomsky hierarchy, which expresses the main relationships between the different classes that we have discussed so far. And the main results: existence of a non-recursively enumerable language, halting problem is not decidable, membership problem is not decidable, problem is not decidable, and closure properties. And there is one very important, interesting closure property, and that is if L is recursively enumerable and complement of L is recursively enumerable, then this implies that L is recursive. So that's a very important closure property. And in particular from this, you can revisit the existence of non-recursively enumerable languages. And it follows that, for instance, halting problem, so the language which can be expressed like this, encoding of a Turing machine M, string W, such that M holds on W. So this language, it is recursively enumerable, but it is not recursive. That's one of the things that we established. And so its complement, so let's say this is L1, this is L2, such as MW, where M doesn't hold on W. This language is not recursively enumerable, whereas this language is recursively enumerable, but it is not recursive. Okay, and the reason that L2 is not recursively enumerable is because if it was recursively enumerable, then this would imply that L and this complement are recursively enumerable. So by this fact star, L itself would be recursive, but we know it's not. Okay, so this was a super fast overview of just topics. And the whole point of this overview was essentially to highlight the main topics that we studied. Of course, each topic you can dive into it, solve a lot of problems, and look at how it works. Okay, so there are a few questions. Let me see. One question from Antonia. There is no point for L21. Is this on the final? I am not sure I understand the question. You will have full 3 hours to complete the final. Church-Turing thesis. Sure, Church-Turing thesis is, of course, also a topic that we covered. But there are not that many questions we can ask about it. And it's fairly easy to remember what it talks about. Essentially, it's a hypothesis, which we can never prove, but we could potentially disprove, but it's a fairly strong hypothesis. There are no challenges to it, saying that anything computable mechanically in principle is computable by Turing machines. Can we expect any problems on context-sensitive grammars, unrestricted grammars? Well, you should know the definitions, but I wouldn't expect too many problems on this. Can you explain why, when given context-free grammars G1 and G2, whether L of G1 is equal to L of G2 is undecidable? So this, I would probably revisit this question at the end, if there is time for this, because I have some questions that I wanted to go over. I think they would, that I should kind of try to do it in the order of topics covered. If L is RE, does that make L complement non-RE? No, not necessarily. But if L is RE and its complement is RE, then the language is in fact R. And every recursive language is also recursively enumerable. So there you go. Okay, so before we go further, I would like to say some strategies for the final. So first of all, I suggest that you read all the written answer questions carefully. And you can read them first. It doesn't take too much time, so you'll probably spend, say, 3-4 minutes just reading the questions. And then you attempt them in the order in which you consider the questions to be the easiest. So you start with the easiest question, you write an answer for it. You go to the next easiest question, you write an answer for it, and so on. There are several reasons to do it. First of all, this strategy maximizes the number of points that you obtain, because you don't want to skip an easy question and then think, I'll come back to it towards the end of the exam, and then you don't have time to come back to it. And then you say, okay, I knew how to solve it, but I didn't have time. Well, get all the easy questions right out of the way at the very beginning. And there is also a psychological reason to do that. When you first start, you might see, oh my God, there are a lot of questions, what do I do? But if you take care of several questions that you consider easy, you already mentally count, okay, I have 3 points here, 3 points here, I already got a third of the exam, and that calms you down. And then you're able to perform more optimally going forward. So always get easy questions out of the way first. Now, for multiple choice questions, here is my suggestion. So read every possible answer. Don't just find one answer that you think is correct and then move on to the next one. Read all of them, because maybe while reading one of the other answers, it makes you question, oh, they're kind of similar, and what's the difference? And then maybe you overlooked a detail, so you need to go back, reread the question. Each multiple choice question will have 4 possible answers, and exactly one is correct, or at least it's supposed to be. So you would essentially, you have a couple of approaches. Either you search for an answer that is correct, and then you make sure that it is correct. Or if you cannot find an answer that is correct, you find all the answers that are incorrect. And then the only remaining possibility should be correct. So it might be, by the way, for these questions, you should use the space provided to write possible solutions. So for instance, if you see an NFA given to you by a transition diagram, something like A, B, and you have a state Q0. If you're reading A, maybe you go to Q0. If you're reading B, you go to Q1, Q2. If you're in Q1, you're reading A, you go to Q0, Q1. And if you're reading B, you go to Q2. And then something like Q2, if you're reading A, it goes nowhere. If you're reading B, it goes back to Q2. And you're told that Q0 is the initial state and Q2 is final. So you probably won't see this exact transition because I just made it up. But I'm trying to illustrate the point. You see this transition, and it's kind of difficult to know what this NFA is doing. I have no idea how it works, really. I was kind of filling it in randomly. But you have some free space. So construct a diagram for it. Most likely, it's not one question about this NFA, but the follow-up question is also about this NFA, maybe a third question. So there might be several questions about this NFA. So you want to have a more kind of visual representation, which is easier to understand than just a table. So you spend some time drawing it. Okay, you have a state Q0, that's your initial state. On A, you transition just to Q0, and on B, it goes to Q1, and there is also Q2, which is also a final state. So on B, you can go like this. Now, from Q1 on A, it can either go back to Q0 or it has a self loop to Q1. And on B, it goes to Q2. And now in Q2, you have a self loop on B back to Q2. So that's kind of your NFA. And essentially now it is much easier to see what is going on. So in particular, if you're trying to decide what is the language of this NFA, you observe that kind of needs to end in a B. And then you just need to verify whether every possible string that ends in B is accepted by this NFA, or there are some strings that are not accepted by this NFA. So some strings are not accepted by this NFA that end in B. For instance, BB, AB is not accepted by this NFA. So you need to spend some more time to analyze it, but at least you learn some partial information right away from this drawing. So don't guess at the answers, try to actually solve them. And if there are questions which talk about closure properties, so closure properties, and there could be many different questions, remember that you might be given a whole bunch of different languages, like L1 is regular, L2 is recursively enumerable, L3 is context-free, L4 is finite, and so on. And then you're asked about some crazy combination, L1 intersection L2 dot L3 is something, is context-free or whatever. And you want to see if it's always true, or there are examples where it actually is not true. The information provided that L1 is regular, L2 is recursively enumerable, and L3 is context-free. It is not enough to conclude that this is context-free. So if you want to construct a counterexample to a given claim like this with closure properties, your friends are your corner cases. So remember that you have these kinds of languages, which are empty set, you have language containing lambda, you have sigma star, and these are essentially your corner cases. And with these corner cases, you can usually construct counterexamples pretty easily. Like for instance, concatenation takes precedence. Concatenation goes first. So
just
for
as
instance,
just as a reminder, sir, sigma star is the set of all languages, right?
The set of all strings.
All strings, right?
Yeah. The set of all languages would be 2 to the power sigma star. So that's
right, and that's uncountable if I remember the notes correctly. Yeah. Okay.
And the important thing about all these corner cases is that they are regular. They are context-free. They are recursive, and they are recursively enumerable. They belong to everything. So these corner cases, they're your basic building blocks for constructing counterexamples. So let's see if we can disprove this claim that just because L1 is regular, L2 is recursively enumerable, and L3 is context-free, that the resulting intersection is context-free. Okay, so first of all, out of these 3 languages, the language that might prevent the result from being context-free is the language L2, because you can have a recursively enumerable language which is not context-free, such as A to the N, B to the N, C to the N. If that's the case, then you kind of want to arrange languages L1, L3 so that the result of this is just the language L2. So if you take L1, so I should say that this claim is false, and the counterexample is as follows. So if you take L1 to be sigma star, L1 is regular, and intersecting with sigma star is not going to change the answer. So the intersection doesn't do anything. And then if I take L3 to consist of just lambda, concatenation with lambda doesn't change the language. So under these conditions, what we have is L1 intersection L2 dot L3 is just equal to L1 is sigma star. So sigma star intersectional language leaves the language the same as it was. And when you concatenate with lambda, it leaves L2 intact. So you recover just L2. So if L2 is any recursively enumerable language that's not context-free, then this L1 intersection L2 composition L3 is not context-free with this choice of L1 and L3. So L2 is any recursively enumerable, but not context-free. So these corner cases are extremely helpful. You can, once you get familiar with using them, you can answer these questions very quickly by providing these counterexamples. Okay, I see Daniel has a question. Please go ahead, ask the question.
Oh, no, I already asked it before. My
oh, okay, it's from before. All right. Are all finite languages regular? Yes, they are regular because you can write an NFA for them. Okay, so next I'm going to go and solve a bunch of prepared questions. And feel free to raise a hand at any point, ask a question. So I see Christoph has a question. Go ahead.
Yeah, I just wanted to be sure, is sigma plus also one of the corner cases?
Yeah, sure. You can consider it to be one of the very useful languages to use to check a certain statement.
Okay, thank you.
You're welcome. I see I get a lot of different questions here. Is every language a subset of sigma star? Yes, that's a definition of a language, a subset of sigma star. Do recursive enumerable languages have closure properties? Yes, they do. So if L1, for instance, and L2 are recursively enumerable, then their intersection is also recursively enumerable. Is it necessary to make a trap state in a DPDA? No, it's not necessary. It's not part of the definition. Couldn't we just say that we promote L3 to be recursively enumerable, and thus, since L2 and L3 are recursively enumerable, they're closed under concatenation, and it is closed under regular intersection. And thus, the result will be recursively enumerable, thus not context-free. Well, in this argument, it wouldn't quite work because if you promote two languages to be recursively enumerable and you take their composition, the result becomes recursively enumerable, but you need to argue that the result is not context-free. And that's not the case. Sometimes you can concatenate a complicated language with another language and destroy the complication. So for example, if L is recursively enumerable, but not recursive, and you want to see if L and, for instance, L2 is context-free, you want to see if L concatenation L2 is recursively enumerable, but not recursive. And that's not the case because L2, for example, counterexample, L2 could be an empty set. Empty set is context-free. You can write a context-free grammar for it, or an NPDA without any except states. And then if you take L and compose it with L2, you get an empty set. And this is even regular. So just because you took a complicated language and you did a concatenation, it doesn't mean that the result is necessarily complicated. Concatenation can destroy the complication in the language. Okay. So let's do this exercise, and the exercises will become progressively more complicated. So I kind of selected a few problems roughly in the order in which we covered the topics. So first exercise is about just general languages. So here we have an alphabet on 3 characters, A, B, C. And the question is, how many strings are there in sigma plus minus sigma cubed times sigma star? So here, the way that we can look at sigma plus is that it is a union of sigma to the power 0, sigma to the power 1, sigma squared, sigma cubed, and so on. It's this infinite union. So your sigma 0 can, I'm sorry, there is no sigma 0. That's why it's sigma plus, not sigma star. So it starts at sigma to the 1. So sigma to the 1 consists of all strings of 1 character, and there are only 3 such strings. Then sigma 2 consists of all strings of actually 2 characters. So you can have AA, AB, AC, BA, BB, BC, CA, CB, CC, and so on. So the size of each of these you can actually calculate very easily. It is the size of sigma to the corresponding power. So size of sigma squared is 3 squared. So there are 9 strings here. And what is contained inside sigma cubed concatenated with sigma star? So this looks like this. We have sigma cubed, and we concatenate it with sigma star. And sigma star consists of sigma to the power 0, union sigma to the power 1, union sigma to the power 2, and so on. So here, this you can actually simplify in this case. So this becomes sigma cubed, union sigma to the power 4, union sigma to the power 5, and so on. So we're interested in strings that are in here, but not in here. So sigma plus consists of all powers of sigma starting with the first one, and sigma cubed concatenation with sigma star consists of all powers of sigma starting with sigma cubed. So essentially every string from this point onward in our sigma plus is going to be present in sigma cubed sigma star. So these strings do not appear in the difference. So the only strings that are in sigma plus but not in sigma cubed sigma star are the strings in this part of our language. And we have 3 of them plus 9. So the answer is 12 strings. Okay, any questions about this problem?
I have a question.
Sure.
Why is it that concatenation of sigma cube with sigma star removes sigma 1, 2, 1, 0, 1, and 2?
Well, because sigma, so you can just look at this expression. Is this equality clear? Here I'm just re-expressing sigma star in terms of individual components of which it consists. It consists of strings of length 0, strings of length 1, strings of length 2, and so on. So this is just by the definition of the sigma star. I'm just rewriting sigma star in terms of what's in brackets. And next, when you concatenate the things here, how does concatenation happen? You take a string from the left language and a string from the right language. String from the left language always has 3 characters in it. string from the right language, these brackets, has 0 or more characters. So what happens when you concatenate a string of length 3 with a string of 0 or more characters? You get a string of 3 or more characters. So that's why you get sigma 3, sigma cubed, and so forth.
Okay. Okay. Thank you.
Make sense?
Yeah.
All right, good. All right, we jump to exercise 5 because I kind of took some random exercise from different places. True or false? Let L be some language over sigma. If L star is finite, then all languages over sigma are regular. And this is a good demonstration of the principle which I was explaining before. Remember the corner cases when you talk about some kind of closure properties. And this is a closure property question. It says, okay, you have a language L, which is a subset of sigma star, and what you know, so this is what you're given. And what you're also given is that L star is finite. And conclusion is that for every L prime subset of sigma star, L prime is regular. So one way to see that this is false, so this will end up being false, is to consider those corner cases that I was speaking about. So for instance, if you take L to be equal to the language containing lambda, then L star, well, this language is a subset for any alphabet. Over any alphabet, this is a valid language, essentially. So L star, in this case, and in general, it is defined as L to the power 0, L to the power 1, union L squared, and so on. But each of these powers is just the language lambda. So what you end up having is lambda, union, lambda, union, lambda, and so forth. So it's just an infinite union of lambdas, but we don't care about repetitions. So what you get is lambda. And this is finite. But sigma was arbitrary. So in particular, if our sigma is even contains one character, but let's say, for instance, 2 characters, then L prime, which is any non-regular language, such as A to the N, B to the N, it is a subset of sigma and it is not regular. So the conclusion doesn't follow. Just because you have some language whose star is finite doesn't mean that every other language is regular. So you have this kind of corner case whose L star is always finite, and it always works for any sigma. And for sure, there are other languages which are non-regular and so on. So you learn no information about other languages by this given information. Okay, any questions about this? Could you have picked null set? Yes, you could have picked null set. Another approach or another counterexample. If you pick L to be an empty set, then L star is going to be, again, lambda, the language containing lambda and only lambda, and it's finite. So L prime, any non-regular language. Yeah. If you take any alphabet, sigma L equal to the lambda is also a language over that alphabet. That's correct. Yeah. Is the bottom right sigma? Yes, it's supposed to be sigma star. Thank you. All right, so next question. Design an NFA for this language. So you might recognize this as a worksheet problem. So it's AB to the power I union BA to the power I, where I is greater or equal to 0. So what are the strings that belong to this portion of the language? Well, it starts with lambda. The next shortest string is AB. The next string after that is AB, AB, and so on. And the strings belonging to this language, they start with lambda, then the string BA, then BA, BA, and so on. So either you have a sequence of AB repeated or a sequence of BA repeated. You cannot mix and match AB followed by BA. That's not allowed. So for this, we can start with our initial state, let's say Q0. And if we see an A, we transition to Q1. And this indicates that we should be seeing this pattern AB repeated. So if we see AB, we go to Q2 and we accept. If we see an A, then we go back to Q1. So the only way to accept if you take the A branch is to do some number of these AB sequences. That's how you can get to Q2 and stay in Q2. Now, if the first character is B, you go to Q3, and then you should see A, then you go to Q4 and you accept. And if you see B from Q4, you kind of repeat it like this. Is this the whole NFA, or is something missing? Aha, lambda is missing. Q0 should also be a final state. Very good. So Q0 should also be a final state like this. And then, indeed, lambda gets accepted in Q0. And if it is not lambda, then in the top branch, we need to have at least one AB. And after that, we can keep repeating ABs. And in the bottom branch, we need to see BA. And after that, we need to keep repeating BAs. So that way we can take care of these two languages. Another way to solve this question would be to design an NFA for the first language in the union, design an NFA for the second language in the union, and then create a new initial state and have a lambda transition. So that's also a valid approach. But I'm kind of spending a bit more, I'm avoiding lambda transitions because of the next part of the question. The next part of the question asks us to convert the NFA into a DFA using the conversion procedure. What would be the minimum number of states in an equivalent DFA? Well, that requires some thinking to answer. It's not as simple as immediately answering it. It might be that you might need 5 or 4. You need to see if you can do 4 states and so on. Okay, so there is a question, is it not already a DFA? And it is not a DFA because, for instance, we don't have a transition, a transition from Q1 on A defined. We don't have a transition from Q2 on B defined, and so on. So this is not a DFA. No transition delta Q1 A. So our delta function is not total. So one suggestion is just add the reject state with an infinite loop and make a transition that way. Yes, I could do that. And indeed, that's what this conversion procedure will do. But if you are asked to carry out the conversion procedure, you should do what the conversion procedure does. Not just kind of complete it to a DFA the way you think it should go. Will the conversion procedure discover the same DFA? That's what we need to see. But also, I think this is a good opportunity to review what the conversion procedure would do. In this case, it would actually do what is expected to do. But in general, the conversion procedure has names for states which are subsets of states of the original NFA. So we start out in a state that contains just Q0. And because Q0 is an accept state, this would also be an accept state of this DFA. On transition A, we go to state Q1. And on transition B, we go only to state Q3. So here, it behaves exactly like our DFA was behaving. Q1 on B goes to a state Q2 only, which would be an accept state. And on A, it doesn't go anywhere, which means that the set corresponding to it would be the empty set. And the conversion procedure from the empty set on AB, it goes back to itself. So it's a trap state, actually. Now from Q2 on transition A, we go back to the state Q1 only. And on B, we go to a trap state. On the other branch, on A, we go to a state Q4 only. And then on B, we travel back. And this transition on B is defined like this. And this transition on A is defined like this. Yeah. So in this case, we didn't actually create all that many new states, but for instance, our NFA had only 5 states, but our DFA now in this example has 6 states, 1 extra state. Okay. Any questions about this?
Yeah, I had a question.
Yeah.
Let's say we have like some sort of lambda transitions that get really complicated. The states are going to be it's a set of states, right? Like it could have more than one state inside.
Yeah, even without lambda transitions, that is possible. So maybe I should just show some example like that. Well. Sorry, you had, I'm not sure if you completed your question.
Yeah, it was just to say like the states, like they get, like there's going to be like 2 or more states inside one state, like would be the set of states.
Yeah, so let's do something where it does happen. So for instance, you might have Q1, Q2, Q3. So something like this. So this is your NFA, and it essentially consists of all strings that end in BBA. So now here, we would create some states which are labeled by multiple states from the original NFA. So when we convert it to a DFA, we start out by considering what happens in the initial state, the state Q0. If we see A, we just go back to Q0 only. But if you see B, it can go to Q0 or Q1. So because you have two possible states in which NFA can be after you see B from Q0, you need to create a new state which is labeled by these two states. So the meaning here is that if your original NFA was in state Q0 and you saw a B, now your NFA could be either in Q0 or in Q1, and that is a new state in your DFA. And if you had lambda transitions, as correctly pointed out in the chat, you would need to consider which states you can use also by taking lambda transitions. So you take a lambda closure of the set of states. So if you, for instance, had a lambda transition from Q1 to some state Q4, you would go not only to Q0, Q1, but also Q0, Q1, Q4. Okay, now if you're in this state Q0, Q1, and you see A, how do you know where to go? So for this state, we want to define what happens on A and what happens on B. So Q0, Q1 on A. How do we find it out? Well, we first see what if we are in Q0 in our NFA? Where can we go on A? Q0 on A can go only to Q0. And what if you're in Q1 on A? Q1 on A doesn't go anywhere. It's just an empty set. And then we take the union of these two possibilities. It gives us just Q0. And you see, if you already have the state labeled Q0 in your DFA that you're constructing, there is one. So it means that if you see an A, you should go back like this. Now, we also need to define an arrow from Q0, Q1 on B. We use the same procedure. We first see, what if you're in Q0 and you see B? Well, then you can transition in the original NFA either back to Q0 or you can go to Q1. So you can reach Q0, Q1. What about if you're in Q1 and you see B? If you're in Q1 and you see B, you can transition to Q2. So you take the union of the two, and that defines a new state for you, Q0, Q1, Q2. So we don't have a state labeled Q0, Q1, Q2. We need to create it. So Q0, Q1, Q2. We create this state. And now we repeat the procedure. For Q0, Q1, Q2, we see where we can go on A. For Q0, Q1, Q2 on A, we can go either to Q0 or to Q3. So we transition to a new state, which is labeled Q0, Q3. And if you see B, then actually from Q0, you can reach Q0, Q1. From Q1, you can reach Q2. From Q2, you can't reach anywhere. So the union of all three possibilities leads back to itself, like this. Okay, then we're at Q0, Q3. For it, we need to define what happens on A and what happens on B. Q0 on A, you go either to Q0, or in Q3, you go to an empty set. So the union of set containing Q0 and an empty set is Q0. So it means that on A, you go back to Q0. And if you have a B, then actually you can, from Q0 on B, you can go to Q0, Q1. From Q3 on B, you can go to an empty set. The union of two possibilities is just Q0, Q1. So on B, you go this way. And that completes it, because every state has two arrows, A and B defined, and we don't need any more states here. Now, we only need to decide which ones are the final states, and they would be the final states where Q3 appears. And Q3 appears only in this one. So this becomes our final state, like this. And as I mentioned, if you have lambdas somewhere, always take lambdas and include them. For instance, rather than Q0, Q1, Q2, if there was a lambda transition to somewhere else, you include that state also. So lambdas can be included anywhere. Okay, was this clear? Was it too fast or was it confusing? Let me know. Okay, I'm glad to hear that it was clear. And then when you design the final DFA, you can spend a minute just thinking, does it accept the same language? Because it should accept exactly the same language. The construction shouldn't modify the language. And you can see that the way that DFA works is as follows. We want to accept a string that ends in BBA. So if we see a pattern BBA, we reach an accept state. If after that we see an extra A, then it means that we need to start constructing the pattern from scratch. We again need to see BBA. But if we see a B, we only need to construct BA after that. So essentially, you can see that the meaning of these states is as follows. The first state corresponds to this suffix BBA that we want to construct. It's just not there. We don't have the BBA suffix. Either the string is empty or the string ends in AA. The meaning of this is that the last character was B, and that is the longest portion of BBA at the end that we're trying to construct. The meaning of this state is that our string ends in BB. That's why when you see B's, you keep staying in this state, because if your string ends in BB and you see another B, it still ends in BB, and it keeps going on. And then if you have an A like this, then you accept. So it seems to match. So one of the questions so there are several questions. Do you recommend making a transition diagram for the conversion, or just going state by state like you just did? I'm not sure what the difference between those two approaches were. I was going state by state and I was creating a transition diagram. So to me, it seems like they're the same things, no? Okay, next question. If the NFA has lambda in it, how would we draw the DFA? So, okay, I'll do a short example. Suppose that you had Q0, AB, BQ1, and then you had lambda Q2, for instance, something like this. Then you start with the initial state Q0, you see where you can go on A. On A, you can only reach Q0. So you go back to itself. Then you see where you can reach on B. Now on B, you can reach Q0, you could reach Q1, but you could also reach Q2, because you could consider B to be also B followed by lambda. So when you're constructing the next state, it becomes Q0, Q1, Q2, like this. And then if you consider this Q0, Q1, Q2 state, on A, where can you go? From Q0, you can go to Q0. From Q1, you cannot go anywhere. From Q2, you cannot go anywhere. So the union of those three possibilities is Q0, like this. And what happens on B? If you're in Q0 and you read B, you can reach Q0, Q1, but also Q2. Again, you can also take lambda. So on B, you get a self loop like this. And then you need to consider what is the final state in this diagram. It is a state containing Q2. It would be this state over here. So when you have lambdas, the logic is exactly the same as before, but you just have an option of taking a lambda whenever possible. And you include that possibility. Okay, for every NFA, there is at least one DFA, that's true. But for NPDA, there is not necessarily a DPDA, that's true. So NPDAs are more powerful. Yeah. Okay, very good. Let's go next to regular expressions. So we have the following regular expression: A, B star, A star, A, B star, B, A. List all strings whose size length is at most 3. Okay, so at most 3, which means that the string could have length 0, 1, 2, or 3. So there a string of length 0 is not an LFR because here we have a union of two possibilities. The first language associated to this R1, so to speak, the shortest string here would be A. That is the string of size 1, and no other string of size of length 1 is in LFR1. But we can have strings of length 2 here. And the string of length 2 comes from either using a B from the B star. We can have one repetition of B, or we can omit B and take a single A from the A star. So this is another string of length 2 from R1. And in terms of length 3 strings in R1, we can have A followed by B, if we take 2 Bs. We can have a string A followed by B followed by A if we take 1 B. And we can have a string A followed by AA if we take 0 Bs from it. Now, these are all the strings of lengths 1, 2, and 3 from R1. We also need to do it for R2. R2 doesn't have strings of length 0 because it always contains BA. If we take from the AB star portion at least one copy of AB, then we already would get a string of length 4. So there is only BA possible. So that is BA from R2. And you can also look over the list that you created and make sure that there are no repetitions so that you don't count the same string twice if you're asked to count it. And I think that's it, right? There are no other strings here of length at most 3. So essentially for questions like this, I recommend that you have some sort of systematic way, rather than saying, oh, I see that A isn't here, AB isn't here, and then BA isn't here, and so on. You split this problem into several subproblems. Subproblem corresponding to R1, subproblem corresponding to R2. Then you take the subproblem for R1 and you split it into several other subproblems, like all this length 1 strings, length 2, length 3. If you have some system where you can go over it one by one, it helps you make sure that you don't miss anything. And then you do a final check that you didn't repeat anything more than once. Okay. And next, we're asked to give a finite state automaton that accepts LFR. And here we can, for instance, use this idea that I mentioned earlier. First, we give an automaton for LFR1, and it looks like this. We would have an initial state, we need to have an A transition. Then we can have any number of B's, which is a self loop here. And we can also have a lambda transition, and we can have any number of A's, and then we accept like this. That is corresponding to L of R1. Then we can also do an automaton for L of R2. So we want to have AB kind of cycle going on. We can repeat it as many times as we want. And then we can have a transition BA and accept. So that corresponds to L of R2. And the L of R, we just introduce a new initial state and have a lambda transition to initial states of the two NFAs. So pay attention to the question, because here it says finite state automaton. Finite state automaton means it's your choice, NFA or DFA. And the NFA is easier. So if you have such a choice, go for the easy option. If it says give a DFA, then make sure that what you give is actually a deterministic finite state automaton, because otherwise you would lose points, maybe even all of them. So it's important. But when you're given such a choice, that's good. You just do which one is easy. Okay, so let's look at the next exercise, which is about the choice of a string for the pumping lamp. So here, the language is kind of tricky because it has a regular portion, just A star, B star, and we take a union with a portion which is not regular. It is A to the power I, B to the power J, C to the power K, and J should be greater than I, as well as J should be greater than K. And you're trying to use a proof that L is not regular. M is, again, the constant of the pumping lemma as usual. Which of the strings should you choose as W to be able to derive the desired contradiction? So let's consider these options in turn. Suppose that you chose W to be the string A to the MB. This string belongs to the language, so that's fine. And its length is M+1. That's also fine. But the problem is that when you get to this decomposition, UVX, where the length of UV is at most M, the length of V is at least 1, and you try to pump the V part, what will happen is that you will just increase number of A's. So V consists of A's. Say V is just A to the power K. And then when you consider Wi, UV to the power IX, it is actually M to the power M plus I minus 1K B. So it's of the form some number of A's followed by a B. Because the portion that you pump is at the front and consists of the first M characters, when you try to pump the string, you will be pumping number of A's. And notice that we have this language A star, B star as part of our L. It sits inside. It's a subset. So when you pump, you again get something of the form A star, B star. So it is going to belong to the language for every I. And we're trying to get a contradiction. We're trying to pump and get a string that's not in the language. We're trying to get it outside of the language. So with this choice, although it satisfies the basic conditions that it should be in L and its length should be at least M, When you go and try to pump it, you'll never be able to derive a contradiction. So this choice doesn't work. Then prove by closure properties for the F. Yes, you could prove by closure properties. For instance, you could take this language and intersect it with A star, B star, C star, and then that would get rid of the first portion, kind of. Or you need to insist that C is at least 1. You can try to do that, and that's true, that would work. But it's a multiple choice question. You need to pick one of the answers. And the answer proved by closure properties is not among the 4 options given to you. So we need to continue with the investigation. So essentially, for the same reason, if you understood why A doesn't work, you can also see that B is also not going to work exactly for the same reason. You can never derive a contradiction with this choice. So you need to have the C in there. And now it is down to 2 choices between choice C and choice D. So remember that now we need to satisfy this constraint that J, the middle exponent of the B, it needs to be larger than its 2 neighbors. So this m-1, although it is larger than m-2, it is smaller than m. So this string doesn't work since a to the power m, b to the power m-1, c to the power m-2 doesn't even belong to the language. And belonging to the language and being of size at least m is the very basic condition. If it is not satisfied, then that string is no good. But even if it is satisfied, as we saw, that string might not be good because you cannot derive a contradiction with it. Okay, so we ruled out choices A, B, and D. We can then just simply say, yes, fine. That's the only remaining option. So it works, and move on to the next question. Or you can spend a few minutes and think about why it works. What happens then? Well, if you have such a W, you have a decomposition UVX, where V contains some number of A's. And what you can do, you can pump the number of A's up for long enough, for more than M steps. And then the number of A's will exceed the number of B's. And you would get a string outside of the language. So indeed, this choice C can be used to complete the full proof. Okay.
Excuse me, sir?
Yeah.
Sorry, for this second string, in this case, we're only pumping the portion, so we would say that yi is the one that we're pumping, right?
Because well, I called it V here, but yeah, whichever one you call it.
Okay. Because I'm a little confused that it's amb to the power of 2m, because if we change the value of m, it will still satisfy the language, if that makes sense. So if you choose m1 or m2 or m3 to m infinity, basically, it's just going to it's still going to be satisfied, if that makes sense.
You were talking about part B?
No, C.
Answer C? So for the answer C, it essentially, so your W is like this: A to the power M, B to the power 2M, C to the power M. Because you have C's, the only, in order for it to belong to the language, it needs to belong to the second part. Because the first part consists only of strings A's and B's. It doesn't have C's in them.
Yeah, I understand. But I mean, like,
yeah.
Sorry, I mean, like, if we start with this immediately, just random, like, let's say the question is not even multiple choice and we choose this string.
Yeah.
I don't understand the part, like, how we got the contradiction here.
Yeah, so I'm explaining it towards that. So yeah, there is some decomposition, UVX, or did we use X, Y, Z? Doesn't matter which one you use. So your W is equal to X, Y, Z. Size of XY is at most M, and size of Y is at least 1, right? So your Y consists of some number of A's, where K is at least 1. So now choose the I to be, for instance, M plus 2. What happens then? You take the string X, Y to the power I, Z, and that looks like this: A, M, plus I minus 1 times K, B to the power 2M, C to the power M, right?
Yes.
K is at least 1. So number of A's in the string WI, let's call it WI. So number of A's in this WI is at least M plus 1, because K is at least 1, and I minus 1 is going to be M plus 1, which is 2M plus 1.
Okay.
So you're pumping A's up. Eventually, you're going to have more A's than B's. But the constraint of the language is that you need to have more B's than A's in the presence of C's.
Yeah, okay.
So we get that this WI is actually not in the language, but the pumping lemma says it should be.
All right, perfect. Thank you.
Yeah, you're welcome. Yeah, and I think the question in chat says the same essentially point. Why don't we need to show multiple cases for regular pumping lemma? Norm, you sometimes have to show several cases. So there are examples where you might have several cases, but the main reason why it doesn't happen is because in regular pumping lemma, you have the condition that your decomposition is close to the beginning of the string. So it is this part, XY is at most M. And if you arrange your string such that the first M characters are exactly the same, like here, A to the M, then you only have one case. The portion that you're going to pump is among the first M characters, and all those characters are the same. So your only case is when the part that you pump consists of A's only. If you chose a string where the first M characters sometimes had A's, B's, and other things, then you would still need to show a few cases. So for instance, suppose that you chose a string, something like, so assume M is even, then you could choose a string A to the power M over 2, B to the power M, C to the power M. So you have A, and that repeats M over 2 times. Then you have B, that repeats M over 2 times. Then you have more B's because the total number of B's needs to be M. And then you have C's like this. Now, if you consider what the first M characters are, it is M over 2 A's followed by M over 2 B's. If you were asking about, okay, now we apply the pumping lemma and we talk about the Y could appear only among A's. It could appear spanning the boundary between A's and B's, and it could appear only in B's, like this. For such a choice of W, you would need to show in each of these cases a contradiction. But it's kind of first of all, it probably wouldn't work because in one of the cases you wouldn't be able to get a contradiction. And secondly, even if it did work, you are kind of creating more work for yourself. Usually by choosing W carefully, you can ensure that there is only one case to worry about. In the context-free pumping lemma, you don't have a condition that the repetition, the part that you're going to repeat, will appear towards the beginning of the string. It could appear anywhere. That's why there it is more common to have multiple cases. So, yeah.
Sir, I have a question. I'm not sure where the I-1 times k came from. Can you just go over that quickly?
Sure. So we have Wi, which looks like X, Y, I, Z. So, sorry, W sub I. And remember that W1, which is X, Y to the power 1Z, is X, Y, Z. It is our string W. So it is of the form A to the M, B to the power 2M, C to the power M. So if we pump up like W2, we would have XY squared Z, which is XY, YZ. Remember that if Y consists of A to the K, then altogether X, Y, Z give you M A's. So you have an extra K A's when you repeat it. So you get A to the power M plus K, B to the power 2M, C to the power M. If you repeat it 3 times, X, Y, Y, Z, you would get 2K, and so on. So if you consider the relationship between the index of how many times you repeat and what is in front of K, it is 1 behind. So this can be considered M plus 0K. And pumping down is like A, M minus K. So that is our W0. So if index is 0, here the integer is -1. If index is 1, here the integer is 0. If index is 2, here we're adding 1K. If index is 3, here we're adding 2K, and so on. It's always I minus 1. And if you think about why it is the case, it is because our W1 is equal to W. So when we're extracting the portion that repeats, we say Y is equal A to the K. We're extracting it from the string, which is A to the power M. So you're extracting K from M. When you're pumping up by 1, you need to leave that K in, and you need to pump 1 more time. So that's why you're having W2. The first copy of Y is just the part of your regular A to the M from which you extracted it. Then you repeat it 1 more time, you get an extra K.
Yeah, I see. Thanks a lot.
Okay, you're welcome. For the pumping lemma, why do we need to prove all the cases? Well, because if you don't prove all the cases, then your language might be regular. And the reason is that essentially, remember how it works. So you choose W, and you want to show for every decomposition. And you choose I. And you derive a contradiction. So Wi is not in the language. Why is that? Because you're contradicting the pumping lemma. Pumping lemma says for every, so this is pumping lemma statement. Pumping lemma statement. And then application of the pumping lemma for a proof by contradiction. So pumping lemma says for every W in L such that length of W is at least M, there exists decomposition for every I, we get that Wi is in the language. So that's the statement of the pumping lemma. Keep these two things in mind. There is a statement and there is a way we apply the statement. And because we apply it by contradiction, all the quantifiers are flipped. We're trying to prove that the pumping lemma wouldn't work. We contradict that statement. So the pumping lemma says for every W, there is a decomposition such that it doesn't matter how you pump it, you stay within the language. If you want to show a contradiction to this statement, what do you need to do? You need to fix a W. You need to show that no matter which decomposition you choose, there is I, which takes you outside of the language. That's how you contradict the statement. Why does it contradict it? Because if you chose a W, and there is one case, one decomposition for which you cannot get a contradiction, well, that's what pumping lemma said. So you don't contradict it. So that's why you need to show in every possible case, you can show that there is a way to get outside of the language. Can you choose I equal to M? You can. You can even choose it to be equal to M factorial. And there are some examples where you need to do it. Okay, so let's consider the next question, which is quite tricky. So why do I say that this question is tricky? Recall the question L prime, where you have WW, where W belongs to AB star. So this language is not context-free. This is one of those examples which are classical examples of a language or prototypical examples of a language that's not context-free. And the problem here is that the stack, it is kind of first in and last out data structure. So it reverses the order for you. You can recognize WW reverse, but if you don't reverse the second component, you cannot do it with the stack anymore. So that's kind of an intuition, and then there is a proof using pumping lemma for context-free languages. Okay, so L prime, where your string has even length, and if you split it into two halves, the first half is equal to the second half, this language is not context-free. This question says, what if you have a string, which is again of even length, you split it into two halves, X and Y, and now X is not equal to Y. Is it context-free or not? And if you consider L prime not being context-free, you might think that, oh, L is also not context-free. If you couldn't verify that two halves are equal with the stack, how are you going to verify that two halves are not equal with the stack? That's kind of strange. So a reasonable guess is that it's not context-free. But turns out that it is context-free. And that's the weird part. Okay, so it is context-free. And that requires decomposing the string XY slightly differently. We'll look at the string slightly differently. So what does it mean? What does it mean? X is not equal to Y. Well, consider X consists of individual characters, X1, X2, X3, X4, so on, up to Xn. Y consists also of several characters, Y1, Y2, Y3, all the way up to Yn. So if we want these two halves not to be equal to each other, it means that there exists an index I such that xi is not equal to yi, right? So we have that, for instance, x3 could be A, and y3 could be B. So now, based on this index where two strings are different, we want to see what is the relationship between the remaining portions of the strings. And observe what happens. We have two characters here. Then we have n-3 characters here. We have n-3 characters here. And we have two characters here. Okay, but we're kind of splitting it along the y portion. But the important thing is that the summation of the number of characters here plus here, it is equal to the same as the number of characters here. So here we have n-1 characters. And together, the two, let me use blue portions, they also have n-1 characters. Okay. So rather than splitting it like this, where we look at this string according to the middle, instead, let's look at this string as follows. We have two characters here. Then we have a character x3, which is going to be different from y3. And we consider two characters from this side of this character A. Then we have then we have n-3 characters to the left of the y3, followed by n-3 characters to the right of y3. So rather than splitting it in the middle, I kind of made the two positions where the strings were different to be surrounded by the same number of characters. And that decomposition always works. And if you look at this decomposition, now it looks like something you can generate by a context-free grammar. Why? Because it looks like this. You have character A followed by some number of, so let me write it like this now. So we have W1, A, W2, Z1, B, Z2, where length of W1 is equal to length of W2, and length of Z1 is equal to length of Z2. So we have Wi, Zi belong to AB star. This is an alternative representation for a string of even length, where if you consider left half of the string and right half of the string, there will be a difference in one of the characters. But it's only a difference where in the first half, we guarantee there is an A at the position, and in the second half, we guarantee there is a B at the same position. We can also flip it around and guarantee B in the first half and A in the second half. And this would cover all the possible strings which are different from each other. Yeah, there is a question.
In the case you showed now, where it's the length of W1 and W2 and Z1 and Z2 are even or the same, doesn't that limit the possible? No, I'm just having a hard time picturing it. Why is it specifically that it's not W1 is equal to Z1 and W2 is equal to Z2 versus W1 to W2?
Well, it's simply due to the fact that the number of characters in between the two strings is equal to the number of characters outside the two strings. Inside between the two positions. So we have a position x3, y3. The number of characters in between these two positions is exactly equal to the number of characters outside those two positions. So you can represent the string in two different ways. One way is to have the first half and second half. And another way is to take the portion of the string where the third character is in the middle, and then the character y3 becomes the middle of the remainder of the string. So,
okay, yeah, I see what you mean. It just took me a bit of time to wrap my head around it. Thank you, sir.
Yeah, but I think an example might clarify it, because I'm also, I guess, not explaining it very well. So here is an example, for instance. Suppose that this is your x. No, actually, I want, yeah, this is your x. So example. And your y might be something like this: A, B, A, B. This is your y. So this is one decomposition. And why is this string, why is this in the language, in our language L? Well, it's because for this decomposition XY, we have that the second characters are different. So now I'm going to take exactly the same string AAB, AB, AB, AAB, and I'm going to look at it slightly differently. I have this character A, which is different from this character B, which ensures that X and Y are different. I'm going to take the portion of the string where A appears in the middle, and then observe what happens. For the remainder of the string, B becomes the middle. So in this kind of decomposition, our W1 is A, our W2 is B, our Z1 is ABA, and our Z2 is AAB. And then this string becomes W1, A, W2, Z1, B, Z2, such that length of W1 is the same as length of W2. So we took this, the portion of the string where the character, which is going to differ from the corresponding character in the second half, it is centered in that portion of the string. That's why size of W1 is equal to size of W2. And size of Z1 turns out to be equal to size of Z2. And you can always do it. Every string that is XY, where X is not equal to Y, has an alternative representation where the different characters are the corresponding middle portions of the substrings. Except I only shown one case where you have A appearing first, followed by B. You can have another case where you have B followed by A. So if you understand this decomposition, now we can write down a grammar for it. So a grammar for G. So with S, we need to ensure that we either generate A in the middle, followed by B in the middle of a string, or we generate B in the middle of a string followed by A in the middle of a string. A in the middle of a string means that we can either generate A on one side, A on another side, A on one side, B on another side, B on one side, A on the other side, B on one side, B on the other side. And the only way we exit this loop of generating a thing is to generate A. And B is kind of similar. So except when we exit the loop, we ensure that we generate a B. B, 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 or B. So this is our grammar. In particular, if you want to generate this string, for example, let's see how this string is generated by this grammar. So I know that I want to generate a character A, which is going to be different from a character B at the same position, which means I need to use this rule, A followed by B. So I generate AB first as a sentential form, and then I want to generate this blue substring. So I want A to be surrounded by A on the left, B on the right. Well, I have such a transition from A, I can surround A with A on the left, B on the right. So I apply that rule. I go like this. And then I place A in the middle. So I get A, B, followed by B. Now I have generated this blue portion, which is exactly the same blue portion as here. So afterwards, I need to generate the B portion. And how do I generate the B portion? Well, I look at what characters I need to be surrounding the middle B with. I need to surround the middle B with A on the left, B on the right. So we have A, B, A, B, B. Then I need to surround it with B on the left, A on the right. B on the left, A on the right. And then I need to surround it with A on the left, A on the right. A, B, A, B. And then I exit the generation procedure by generating the B. And so this is the green portion, which matches this green portion. And this is the blue portion, which matches that blue portion. And now, if you consider the decomposition into two halves in terms of X and Y, indeed, this part, which we kept in the middle, we ensure that it is going to be a different character. A is different from B, so X is not equal to Y. Okay, what is the question, Alexandra?
Doesn't this work only if you have an even amount of length? Let's say, like in this case, well, what if your first string was just AB and then your second string was AA, for example? How would you generate that? Like your X was AB and your Y was AA, or does it? Because what I see is that it can only, like, it generates A and B's on the left and the right, and then it puts an A in the middle, so it doesn't deal with the fact that if, like, the whole transition of A is only an even number.
Okay, so I might need to add another transition. So you're saying something like AA followed by AB?
Yes.
Mm-hmm. Yeah, so that's true. We would need to modify it. That's a good point. So let's have a look how to fix it.
No, for that specific string, it works because you generate one A and the B just generates a B.
Oh, yeah, that's true. Okay, good point. So we can take this and where the center is. Yeah, that's where we need to locate the center. So this is going to be our blue portion, like this, and this is going to be our green portion, and it's going to work. Yeah, that's true. So we get A, B like this, and we have A, B, and we have A, B, and this is how we generate A, B. Yeah, so you can generate even or odd, doesn't matter. Okay, very good. Yeah, I thought it was a complete grammar, but for a second I was confused. Very good. Any other questions for this part?
I have a question that is not specifically for this question, but related to context-free languages.
Mhm.
So in assignment 4, we had language equal W hash U, where W is a prefix of U. And it was not context-free language, we proved it. But what if you had L equals WU without the hash, and W is a prefix of U? Will it be like you give the NPDA the ability to guess the prefix, I guess? Would it be a context-free language?
Well, this would be in fact regular, because this is just equal to sigma star. Because if you just want to ensure that there is a W prefix of U, W could be lambda, and lambda is a prefix of every other string. So this becomes sigma star, which is actually regular.
Okay, perfect. Thanks a lot.
Okay, you're welcome. Okay, so there is a conversion of a grammar into a CNF question, but there is only 10 minutes remaining. And I have actually a lot of questions planned. Let me see, a Turing machine question might be good to do. I think that would be like more on a later portion. So let's see, I cannot stay for too long. I might be able to extend the session a little bit over time, but not much, not more than, say, 10 minutes. Okay, so let's look at this question where we try to design a Turing machine to compute the language, the function f of x equal to x mod 5. And here x is represented in unary. And first, it is good to actually first come up with a high-level strategy. So suppose that we have our input, something like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is an example for 12, and we want to compute what would be 12 mod 5. So there should only be 2 ones remaining. Will there be any questions like this in which x will not be in unary? It's possible that we can ask you about where x is in binary, but for instance, if you're doing division by 2, it's even easier. So then in unary. But most of our Turing machines are in unary. So it's a very low chance. Yeah, if it's a binary, you just erase the last bit. Okay, so for something like 12 mod 5, one possible strategy is that the machine needs to count 5 ones in the input and mark it. So one possibility is to say, okay, I've seen 1, 1, 1, 1, and then the 5th one, I'm going to mark with a 0, overwrite it. Then I'm going to go 1, 1, 1, 1, and I'm going to overwrite it with 0. And then I go 1, 1, and I see a blank. And what I need to do now is I go to the left and I want to erase everything past the 0. And that would give me 1, 1, which would be what we want. Except we cannot just erase everything past 0 because maybe our number was divisible by 5. And we need to be able to get back to the beginning of the output. So if we just simply go to the left and we kind of erase this part in orange, we can have a loop where when we encounter a blank and suppose that we erased everything. So it is all blanks and we have 1, 1 and blank. And we have reached here. Now we need to come back to the output. This because the way that transducer is defined, when you terminate, you need to be pointing to the first character of the output. So if we just use this strategy and we erase everything beyond 0, well, we can try going to the right until we hit the first one, and then we terminate. That works, except for the case when x mod 5 is actually 0. If we simply erase everything to the left of 0, and our integer was divisible by 5, then you would erase everything. You would just have a tape of blanks. And then when you go to the right to try to locate the first character of your output, you will never terminate. You would enter an infinite loop. So that's the only issue that we need to worry about here, essentially, with this strategy. And the way that we're going to address it is as follows. Rather than doing this strategy, we do something similar. We still go and mark every fifth character with a 0. But then when we hit a blank and we start scanning to the left, we mark the first 0 that we encounter with an X, and then everything after that is essentially remarked with a 0. We hit a blank, and this is the intermediate state of our computation. And at this point, we start going to the right, replacing every 0 we see with a blank. And when we see an X, we know that this is time for us to terminate because we're pointing to the next integer. And even to the output of the Turing machine. And even if the integer X is divisible by 5, this would allow us to terminate pointing to a blank, which we can take as a representation of a number 0 here. So this is an issue with the encoding integer 0 in unary. It's kind of encoded by a blank, and you need to be careful not to enter into an infinite loop. And I think this is kind of the main reason for why the textbook usually prefers not to have blank input or blank output, just to avoid this complication. But you see that it's actually not that difficult to take care of if you're a little bit careful how you design.
Sorry, sir.
Yeah.
So if we are supposed to end up with a blank string, so we won't have any ones, then why doesn't the first strategy work then? For a multiple of 5, it should still work.
Well, the problem is your Turing machine also needs to terminate. And the first strategy, once you scan to the left and erased everything beyond 0, you want to come back to the first character of the output. But your whole tape is blank, so you keep going, and how do you know when to stop?
No, but I mean, like, when you're going backwards from the first 0, so in the case of a multiple of 5, your last number would be a 0.
Yeah.
So from that 0, you're putting blanks until you reach a blank, and then you stop there, because like starting at a blank anywhere is the same. What's the
That's true.
difference?
But then you need to have two different states anyway. That would be another approach. That would also work. But you need to have two different states where the first character is a 0, then you do one thing, and where the first character is not 0 that you encounter upon going to the left. So if the first character is 0, when you reach a blank on the left, you stay there. If it is not a 0, when you reach a blank, you need to return.
Oh, okay.
So it would boil down to essentially the same thing. You still would need to differentiate between these two possibilities. Yeah.
All right, perfect.
Here
Thank you.
it's just a little bit less differentiation, but it's essentially, yeah.
All right, perfect. Thank you.
So we have set 0 to empty. Well, yeah, so 0 in unary is represented by a blank tape, essentially. Yeah. Okay, so let's now implement this strategy. We have an initial state. If we see a 1, we overwrite it with 1 and move to the right. We see a 1, we overwrite it with 1 and move to the right. We see a 1, we overwrite it with 1, move to the right. And we see a fourth one, we move to the right. And now this is the fifth one that we see. We overwrite it with 0 and move to the right. So this process essentially overrides every fifth one with a 0. And these states, they kind of have a meaning. This is 0 mod 5, 1 mod 5, 2 mod 5, 3 mod 5, and 4 mod 5. Okay. In each of them, we can encounter a blank character. So if we encounter a blank character, we need to move to the left. So we encounter a blank character. We move to the left for each of them. So blank character, move to the left. Like this. Okay, so this new state in the middle that I drew essentially corresponds to this situation over here. So actually, no, it corresponds to this situation, and we start moving to the left. So we're kind of pointing to a character here. So what we want to do in this state, we want to skip over the ones until we reach the first 0. So we can either reach a 0, or if a number was less than 5, we would reach a blank. If we reach a blank, then it means that we already have an output. If we reach a 0, we need to exchange it for an X. Okay, so we're in this situation, we're pointing to the rightmost character. On a bunch of ones, we keep skipping to the left. There is a possibility that we encounter a blank. This happens precisely when our integer already was less than 5. So for instance, if it was 3, then we would go from this integer to this integer to this integer. We would reach a blank. We would transition to this state. And in this state, we start traveling to the left. And we encounter another blank. And this happens if and only if the integer that we started with was less than 5. In which case, we go to the right, and it is its own modulus. So we accept. Otherwise, if it's 5 or more, we would encounter it 0. And this is the first 0 that we encounter going to the left. So we're going to replace that 0 with an x. So 0 gets replaced with an x, and we keep moving left. So in this case, over all the different ones that we see, we turn them into zeros, and every 0 that we see, we also turn it into a 0. And eventually we will hit a blank, which means that we have turned everything. So we're now in this situation. This situation corresponds to this transition. We hit a blank and we start moving right. Here, every 0 gets replaced by a blank, and we keep moving to the right until we encounter an x. And when we encounter an x, we replace that x with a blank, and we move right, and this will be our final answer. So this corresponds to this transition over here. Okay, I think this should take care of this question. Is it required that we erase the rest of the input, or can we just point to the right place? It is required that the rest of the string is erased. So the string contains just the output and the blanks outside. So what if we had 5 mod 5? What would be the final output? The final output would be just blank. Is the center state also an accept state? No, it is just me being circling too much.
Excuse me, sir?
Yeah.
I have a question. So in the tutorials, the TAs used a bit of a different representation. So they would, instead of the arrow for the transition, so you'd say 1, 1 right, would be 1/1, comma right. Are we allowed to use that in the exam, or is that like
yeah, that's fine. As well, I mean, usually there are 3 components. There are many different versions that you see. Sometimes people use this. Sometimes people just use this, sometimes this. As long as it's kind of clear what is happening, and you can help me, who is going to be grading it, by saying that, okay, 1 to R is equivalent to 1 to R, for instance. If you write such a note, I'll know that you're just using a slightly different notation and what matches what. Most likely, I'll be able to infer the meaning from your solution, but just in case that I cannot infer it, it's better to provide such a note.
Okay, perfect. Also, for the states at the beginning where you said each state indicates has a meaning, where this is 0 mod 5, 1 mod 5, 2 mod 5, and so on. Like for example, the 4 mod 5 one, how does that work? Because 4 mod 5 should be 4, right? Not 5. So I'm a little.
Yeah.
It's supposed to start right from
4
1.
mod 5 would be like this. This is how you start, right? So your machine would essentially go like this. It will start in the initial state, transition to this state, then transition to this state, then transition to this state, and then transition to this state. It will encounter a blank. It will go here.
Okay.
It will take a self loop 4 times, encounter another blank, and just output the same thing that it started with.
Okay. All right. Perfect. Thank you.
You're welcome. Can we add 0 or $sign after the input is over at the beginning in the Turing machine so that it's easier to draw a Turing machine? Then add 5 ones on the tape and then do the mod operation. I mean, you could do it.
Yeah, like we after the input is we take all the ones, then we add a 0 or a $, then we add 5 ones and then replacing. It's not in case of mod 5 because this is a bit easier. But when it is X mod X or maybe, so in that case, can we do something like that? using extra tape?
Sure, yeah. I mean, there are infinitely many solutions. Some of these things are not necessarily like simplification in my mind, but if you find it easier and it works, then it is a simplification.
Okay, thank you.
You're welcome. Yeah, David?
So in case of unary, are we only allowed to print zeros and ones on the tape, or are we allowed to print any character on the tape? Because, well, the tape language and the input language, tape are allowed to be different. So
you can use whatever symbols you want.
Okay.
As long as you're using finitely many symbols.
Okay. It's just to clarify, it's just the input needs to be in unary and the answer needs to be in unary. Everything in between, we could do whatever we want with, correct?
That's true. Even input and output might be different. It depends on the question. So question would usually specify.
Okay.
Like your input and output is in unary. Yeah.
Because I didn't realize this I did not realize this for the assignment, and so my entire thing is assuming you could only print and or write ones, so that would have been helpful to know beforehand. All right, well, thank you, sir.
Okay. Probably made your life very complicated.
It did.
A question, just small question. I didn't quite get if when you say design a Turing machine, you mean just a standard Turing machine, right? You are not allowed to use double tapes, no two track tape or whatever else.
Yes. Yeah. So if we want you to design something other than standard machine, we would say so explicitly. Yeah.
Perfect. Thank you.
Okay, do we have to know the completeness problem for CFG? What do you mean by that? I will post the annotated slides, yeah, sure, but not all the solutions are in here. Okay, so we have would be undecidable. Given the context, free grammar is L of G equal to sigma star. That a question of this form goes outside the scope, but we can ask questions that are like modifications of, say, membership problem or the halting problem, that kind of stuff. Mm-hmm. Yeah. Okay. Very good. We have a couple more minutes. Okay, so I'll just very quickly point out a few things. It might go super fast. So you might see questions like this, right? So you're given a language and you need to decide whether it's regular, context-free, but not regular, not context-free. And you're asked to prove it. So here, language A to the N, B to the N is not a multiple of 5. Well, it is context-free, but not regular. So suppose that I mark this category. What does it mean to prove that it is context-free, but not regular? You need to prove two things. First, you need to prove that it is context-free. So this language I can represent as L1 intersection L2 complement, where L1 is a CFL and L2 is regular. So L1, which is a CFL, is A to the N, B to the N greater or equal to 0. And the reason that it is CFL, it has a CFG, which is ASA, ASB or lambda. And L2 is the language of the regular expression a plus b, 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 star. So this is regular. Because L2 is regular, it consists of all strings that are multiples of 5. And L2 complement is the strings whose length is not a multiple of 5. And if their length is not a multiple of 5, then 2 times that length is not a multiple of 5. So L is indeed equal to L1 intersection L2 complement. L2 is regular, L2 complement is regular, and the context-free languages are have this regular closure property. So the resulting thing is context-free. So this proves that it is context-free. And the second thing that we need to show is that it is not regular. And this requires pumping lemma. So you assume it is regular. You let m be the constant of the pumping lemma. And so on. So you do the proof by the pumping lemma. So this would require 2 different parts. Next, I want to briefly mention answers to these parts, but I see there are questions. Is the final based much more on the post-midterm material or roughly the same amount for both? It's a bit more on post-midterm material, but it also includes the material before the midterm and the combination. So now we can talk about intersection of a regular language with recursively enumerable, for example. So it's not a clear-cut division. Not every question is only about the first half or only about the second. Many of the questions involve both halves. Can I explain the first one again? So essentially a to the n, b to the n is not a multiple of 5. I want to show that this language is context-free. So the way that I'm going to show that it is context-free is I'm going to use the regular intersection. So if you have a language that's context-free and you intersect it with a regular language, the result is context-free. So I want to find language L1, which is context-free, language L2, such that L1 intersection L2 complement is exactly this language. So L1 is just the language A to the n, B to the n. And we need to get rid of all those n that are multiples of 5. So how are we getting rid of all multiples of 5? Well, I create a regular language which consists of integers whose or inputs whose length is a multiple of 5. And its complement consists only of those strings whose length is not a multiple of 5. So if you intersect L1 with all the strings whose length is not a multiple of 5, you'll get A to the n, B to the n, where n is not a multiple of 5. So it is context-free. Okay, so very quickly, I'll, due to time constraints, unfortunately, I won't be able to get to all the questions, but I'll just quickly do these parts and wrap up here. And so here we have L1, which is context-free, L2 is deterministic context-free, and R is regular. Can we conclude that L1 minus R is a context-free language? In this case, the answer is yes, because L1 minus R is the same thing as L1 intersection R complement. It is exactly the same thing. And it is kind of similar to what we were discussing here. If R is regular, by closure properties, R complement is regular. And then the intersection of a CFL with regular is CFL by regular intersection closure. What about R minus L1? Is it a CFL? Here the answer is no. And as I was saying before, these corner cases provide a lot of insight. So the corner case here would be R equal to sigma star. For this case, we can take L1, which is CFL, such that L1 complement is not a CFL. And we know that such a language exists. So a language which is context-free, whose complement is not context-free. We know that it exists because context-free languages are not closed under complement. If we pick such L1 and we pick R, which is equal to sigma star, then R minus L1 is exactly equal to sigma star minus L1, which is the same thing as L1 complement. And this is not a CFL. Now, L2 is a deterministic CFL, so it is DCFL, and we take a union with R, which is regular. The resulting thing is indeed a deterministic context-free. So this is yes. The answer here is yes. It will be DCFL. And the reason is product construction with DFA. So in a product construction, you create superstates which simulate the operation of your PDA and your finite automaton in parallel. So if you have transition from state Q1 to Q2 on A in your in your DPDA, and you have a transition from say P1 to P2 in your DFA on A, then you can combine them into one superstate and one transition. So you're simulating both things in parallel. So you can always do this kind of product construction. And if you've been attending lectures, you probably saw this construction. I mentioned it 1 or 2 times. And the important thing to observe here is that if your PDA is deterministic and you apply product construction with a finite automaton, which is also deterministic, the construction doesn't introduce non-determinism. One machine is doing its own thing, another machine is doing its own thing. Always steps are well defined. There is no ambiguity how to take a step, what is the next step. So the product construction is also going to behave deterministically. So that's the reason why the answer is yes to C. And for the same reason, the answer is yes to D as well. So this is yes, and this is yes, and the same reason for both. So both parts. You can also do a product construction for the intersection. Okay, LS?
Yeah, sir, I just had a question regarding the exam. How many long questions is there be around? Because I know you mentioned that 2, 3 more multiple choice questions times more.
Yeah.
Do you know around how many questions there's going to be for the long ones?
There will be a few.
Because I saw you ignoring the questions a couple of times in the chat, so I just wanted to see. And also, as you mentioned, someone did mention there's a lot of true or false questions in this slide going on. If you could just literally just tell us yes or no for people maybe to figure it out after, because I feel like it's very good practice. But if you don't have the time, it's understandable. And thank you very much.
Okay. Yeah, so this unfortunately concludes the review session, but maybe fortunately, I don't want to overload you with information. Now, I suggest you spend the rest of today, say, studying, going over the things and so on, but also get plenty of sleep for tomorrow. Sleep is important. Don't forget about these strategies for how to answer questions. Take care of the written questions that you consider simple. For that, you need to read all of them. Try easy things first. Do multiple choice things. Come back to the questions, review them. And yeah, so that's all I have to say. I'll post these slides right away. And that's
if
it.
it's possible to post them with the solution, that would be great. But if it's not, then it's fine also.
Okay. So good luck, everyone, tomorrow on the exam. And I will see you during the exam tomorrow.
Thank
Thank
you, sir.
you.
Have a good evening.
Yeah.
Thank you, sir. Goodbye.
Bye-bye.
Sir, Professor, is the clock going to be projected on the screen? Because otherwise we'll have to bring the watch, because last time the watch was not shown on the I mean, they were noting down the time on the blackboard, so it would be easier if they can project the time duration on the projector.
Okay. It's not guaranteed, but we can try arranging something like that, depending on whether they have access to the projector and it's easy to set up. If it's easy to do, we'll take care of it. If they don't have credentials to do it, then it might not be possible. So, yeah.
Okay.
We'll try to do it, and if we forget, remind me. All right, you can just raise your hand and ask, can you project on the screen, and I'll try to look into it.
Yeah, thank you.
All right. All right, good night, everyone.
Thank you, sir.
See ya.